Okay, so we're looking at office hours. It's week 1. What is it? Winter quarter? Yeah, it's cold outside. It must be winter quarter. Okay. Yeah. So we've got a couple different things we can look at. One person was already asking about unit conversions, and we're just going to make up a couple unit conversions to look at. I'm going to try to make some tricky ones up. We'll see how I do. Okay. Let's see. I'm going to try to pick a really weird one. The mass of the sun. Okay, how silly should it be? Let's do it into 3 different things. Let's do it into pounds. Let's do it into grams. And let's do it into AMU. The mass of the sun in AMU is going to, all of these are going to be silly. Right, so how much does the sun weigh? The sun weighs 1 SMU. That's 1 solar mass unit. I have that memorized because it's easy.
Yeah.
Right, that's the whole point of SMUs. It's easy to use. Now, in order to get how much 1 SMU is, I have to look that up. It would be on your equation. Well, actually, I don't think this one would be on your equation sheet because we usually don't deal with things that are astronomical like this. So let's go ahead and look it up. That is weird. .989 times 10 to the 30. Okay, so it turns out I'm going to do B first because that one's going to be easier. So I'm going to take, the nice thing is I've got 1 SMU that's already equal to that, so 1 sun weighs 1.989 times 10 to the positive 30 kilograms. You'll notice a lot of times in chemistry, we've got negative exponents. So sometimes I'll say minus, and I'm like, oh wait, actually this one's positive, because it's unusual. But so we've got our 1.989 times 10 to the 30 kilograms. And then I know that I have 1,000 grams for every 1 kilogram. And so that's going to be times 1,000, so that's going to give me 1.989 times 10 to the 33 grams. Just a difference of 3 zeros. So that gives us the answer to part B. Now, to get this into AMUs, it's actually going to be easier. We've got a couple different numbers, so I did B right there. It's going to be easier, I think, work from that if I have an. Do I have an equation sheet handy? I think I handed out all of the equation sheets. Does anyone have their equation sheet? Oh, thank you so much. So on the equations sheet, we've got AMU in kilograms. So even though I've got the answer in grams, it's going to be easier to work with the kilograms number. And this is going to be a little silly. I'm going to ask you for that number in just a moment. So I'm going to do C next, where I've got 1.989 times 10 to the 30 kilograms. And then I have to make sure I rearrange that expression the right way. The expression we're working with, I'm going to sneak it in right here. It's going to be 1 AMU equals
1.66 times 10 to the negative 27 kilograms.
So we have to rearrange this expression to get it multiplied by 1. Right? So we're not really changing anything. We're going to multiply by 1. I want to get rid of kilograms, so I'm going to divide this number over, so I have AMUs over kilograms. That will get rid of my kilograms and leave me in units of AMU. So I'm going to have 1 AMU divided by 1.66 times 10 to the minus 27 kilograms. Now, if you have one of those fancy scientific calculators, make sure you get a parenthesis on that. One of the most common mistakes people make is this 10 to the minus 27 ends up on top if you don't have a parenthesis. Obviously, when you write it down, you don't need that parenthesis there, but if you're doing it in your calculator, make sure you get that parenthesis there. Or if you use one of these calculators that has the nice 10 to the power function, that works as well. Now, this is going to be some gigantic, silly, massive number. Yeah?
I had a question about
Sure.
the significant numbers and the rounding. How do you round correctly and for the right answer?
I'm gonna round it then. So you'll notice I'm recording this, so I'll be careful. I'm not as strict about rounding and significant figures this quarter as I should be. It's when I get to upper division classes that I start to get really strict about it. Your other instructors might have different opinions and different thoughts about it. Almost all of the answers that LabPal accepts will have a plus or minus 5% variance. So, you know, depending on who you talk to in math classes, it's like you should be rounding each step of the way. I do my rounding at the end. I also do my sig figs checking at the end. That will introduce a small amount of error because I might be biasing my final answer by not doing that rounding step by step. However, at this level of like good enough model, right, for this class, it's still going to be close enough. In future classes, what's your major? In the future, getting medicines off by rounding errors could be really bad. So there's going to be times in your life where it's like, no, you have to be really careful and not mess up your rounding. Okay. But even most medications have like a tolerance range where it's like as long as you're within a reasonable range, everything will be okay. So we're going to take care of that at the end after we do this calculation. So since since one SMU is the definition, we can imagine that this actually has like some high level of precision, right? And there's a couple places where we have definitions of things, like 1 centimeter cubed being 1 milliliter. I always write that as 1 centimeter cubed per 1 milliliter. And while that looks like there's only one sig fig, because it's a definition, that actually has what we call infinite precision. That 1 centimeter cubed per milliliter doesn't limit our sig figs at all because it's a definition that has like an infinite number of like decimal places behind it, and it's still true. Same thing with the SMU thing. So the place where our limitation is going to come in here is going to be in this conversion that we're using here. So I'm going to be limiting myself to 1, 2, 3, 4 sig figs through this entire calculation. Technically, because I only used the 1.66, here I could probably grab another 2 digits because this number is known to higher precision. But if we're only using 1.66, we're now limiting ourselves to 3 significant figures rather than 4 significant figures throughout the calculation. I'm okay with in this situation, right? There's very few places. There are a few places where I ask for the right number of sig figs, but most of the time it's just make sure you have a reasonable number of sig figs related to what you physically did in the experiment. So we can go ahead and do this division. We get a silly number, 1.989 times 10 to the positive 30 divided by 1.66 times 10 to the minus 27, and we get 1.981977. I'm putting a silly number of digits. We're going to deal with that in a moment, but since we asked about it, I figured I'd do an example. Times 10 to the positive 57. And yeah. Right, now I intentionally left too many digits here. So we could look at this and say, well, what's reasonable? Reporting this 1, 2, 3, 4, 5, 6, 7 decimal places would suggest that we made this incredibly accurate measurement. But we didn't. we didn't make an accurate measurement. And you know, our limitations here, I've got 3 decimal places, I've got 4 sig figs there, I've got 3 sig figs there. So I'm just going to keep these first 3. And I would put this as 1.98 times 10 to the 57 AMU. And that's what I put as my final answer. Now, technically, we made choices. This is the thing that's interesting about chemistry classes, is we get to make choices. We made a choice in how many digits we kept here for our conversion. We made a choice in terms of how many digits we kept here for our conversion. And that's because we were using the equation sheets, right? If we wanted to look up, let's see, what did I want? AG and AMU. If you just Google it, let's do this the other way, right? 1.6605. If you actually go to, if you go to something that's got a really nice, oh, that's too many things. If you go someplace that's got more details, here's the highest scientific precision they have for AMU. It's 1.660539066660 times 10 to the minus 27. So we could have actually chosen to say, hey, we actually need 9 digits of significance on our calculation. We didn't have to have our unit conversion be our limiting factor. We made a choice of saying 3 fig sigs is good enough. We could have kept more significance there. Generally, the reason we don't worry about that is because in this calculation where there was no measurement that we were making, and so there was nothing that was like physically limiting us, it was our choice in the units that limited us, and the unit conversions. Normally, we're like, oh, well, my glassware is only good down to 2 sig figs anyway, so why would I care? Like, I don't need to do those ultra-high precision unit conversions because my physical limitation is the measurement I'm making, not my math. In this case, where it's just math, and I got that math limitation. Okay, I still haven't done A because I was avoiding pounds. I think this one is also going to be easiest from kilograms from what we have on the equation sheet. Is that true? Does the equation sheet have a pounds to kilograms conversion?
I don't think so.
It might have been taken off. AMU to kilograms. Yeah, they took it off. Okay. So let's go ahead and look up. And again, instead of just using the Google search thing, I'm going to go to what is this? I've never heard of that before. Okay. It's got slugs, it's got pounds, it's 2.204623, so we could, if we wanted to, have 1, 2, 3, 4, 5. We've got 6 places past the decimal point if we wanted to. I'm not going to do that many. It is, so here, let me do that here real quick. One kilogram equals 2.204 pounds. Double check, make sure I got my digits correct. Let's go ahead and round it 2.205. Probably could have just done 2.2 if we wanted to, but why limit ourselves? Let's keep those extra digits. So I'm going to take my 1.989 times 10 to the 30 kilograms. We also know this number to higher precision. We know the mass of the sun way better than 4 sig figs. But let's just go with it, right? 30 kilograms. Then I've got to rearrange this properly to get rid of kilograms and to keep pounds. So that's going to be 2.205 pounds per 1 kilogram. And that should get me the answer for that. So like times 2. So it's going to be like 4. 1.989 times 2.205. 4.385. 4 digits, so I'll go 4.386 times 10 to the 30 pounds. It's a heavy. That's heavy. Now, the thing that's funny about this is, I don't know about you, but 10 to the 30 makes absolutely no sense to me. Like, I have no way of conceptualizing that. Let me see here. Yeah, I have no way of conceptualizing that. Is $1 billion a lot of money? Is $1 trillion a lot of money?
Yeah.
This would be, how many trillions is this? This would be, I can't even say a trillion enough times. I would have to say trillion like a couple hundred times to get to how many trillions this is. It's like a trillion. It's just so big that my brain can't make sense of it.
I have a question for C.
Sure.
Were you supposed to multiply 1.989 times 1.66?
No, it was divide.
Oh, okay.
And, oh, did I forget to divide? Or did it just
I'm
come out
wondering,
really
'cause-
similar?
Yeah, I was like, that's so
0.989
similar to it.
divided by 1.66. No, it just comes out. Oh, I missed a digit. That's why. Had a typo. I was off by a decimal. I was off by a digit. And my brain just kind of erased it. Thanks for catching that. Yeah, so I did divide it and I just wrote the wrong thing down on the board. There was an extra 1 in there. It's 1.19819. But it ends up looking really similar still, which is probably why my brain skipped over it. Tragic, because if you did that on LabPal, it'd just be like, you're wrong, and I don't know why you're wrong. That's a really weird number to get. Looks like you forgot to do things. Let me just double check that again. Yeah, it's 1.19819. So it ends up looking really similar if you miss that first one, which is what my brain did. Let's blame the cold. Like my cold and not the cold outside. So that's kind of like mass. We could do the same thing with length, but it really is the same. You want to do some examples with length, or are you okay to move on?
Yeah.
Okay. So length, volume's a little bit different. Should we try some volume ones? How'd you do with the volume ones in class yesterday?
I feel like they went okay. I think
So
there's
go
one
ahead.
of the homework that's like
Number 12?
maybe.
Maybe.
Yeah, I think number 12.
Can you pull it up real quick? We'll take a look at it.
Yeah.
Is it okay if I erase all this in the meantime?
Yeah, it's fine.
I have it on my phone if that works.
Oh, cool. Oh, number 12 or?
Yeah.
This one? Okay. Is that the one you came to ask about as well?
The density or the volume ones, they were throwing me off too.
That's a particularly tricky volume one, right? The volume ones, when we're doing conversions for volume and you're just converting volume to volume, it's not that bad. When you're doing the size of a shape, and you've got to do like the dimensional analysis to make sure you're doing the correct conversions in each dimension, that's where the volume things get a little bit tricky because you've got multiple dimensions. Have you both looked at number 12 yet?
Which homework is that on?
MQ 1.1.
Oh, okay.
I haven't looked at it yet.
No.
You want to read it?
So 100 milliliter graduated cylinder has the following properties. An inner diameter of 23 millimeters, an outer diameter of 25 millimeters, and a density of 2.23 grams per cubic meters.
Oh no, here it is. Okay. I was like, did I lose my graduated cylinder? Okay, so in case you forgot, this is what a graduated cylinder looks like. I can't see from. Right? This is what a graduated cylinder looks like. It's a cylinder. Right? It's got an inner diameter where the liquid goes. It has an outer diameter for the glasses. And it's got marks down the side for how high you're filling it. Graduated cylinder. Okay, it's got different properties. And then what's the question ask?
What is the vertical distance between 1 milliliter divisions on the cylinder? Give your answers in millimeters.
Anyways, yeah, millimeters. So notice we want to know what the distance is between those two little blue marks. Are we expecting it to be a really big value or a really small value? It's pretty small, right?
Yeah.
It's pretty small. Now we're doing this on millimeters. If we did this on centimeters, I would guess it's probably, it looks like it's about an inch between the marks. That would be like 2 centimeters between the marks. So I'm guessing it's going to be like 0.2 centimeters between the marks, which would be like 2 millimeters between the marks. So I always encourage try and find some context so we have an idea of what answer we expect. I'm expecting an answer of like 2-ish if I do this in millimeters. Now, how am I actually going to find that? Talk to each other. What do you think you're going to do?
I think you can set the volume equal to 100 milliliters, right? And then
We can do even better than 100 milliliters. 100 milliliters would be the whole thing. We just want to find one division. It's just one milliliter. Right? So it turns out we know explicitly we want a volume of 1 milliliter. We know that. Now, how else? There's some information. So I like to do my thinking in these 3 things. We want to know the height separation between the marks. That's what we're trying to get for a result. The explicit information we're given, the only explicit information we need so far, actually, we need that inner diameter as well.
The inner diameter is 23 millimeters.
Right? And then there's some information that's implied. It's a cylinder. What's the volume of a cylinder?
diameter pi times height.
Because it's, what is it? It's pi, isn't it? Because it's 2 pi rh, so it's just d. Because 2r would be d.
Oh.
Yeah. No, I'm sorry. I just remembered it's 2 pi rh. But you're also correct. D pi h is also correct.
Okay.
Great. Okay. So that's our volume. So turns out once we have these 3 bits of information, it's actually pretty straightforward. The thing that makes this problem doable for me is having this like physical reality of like, oh, it's a cylinder that's going to be a 1 milliliter volume cylinder. And I've got to figure out how tall that is given how the diameter. Obviously, if it was a much narrower cylinder, if this was like a really skinny cylinder, that distance would be a lot bigger. If it was a really wide cylinder, that distance would be a lot smaller. For this particular diameter, there's going to be a particular height associated with it. So the thing we've got to be careful about as we start to plug this in, so I want to solve for h. So I'm going to get v d pi equals h. That's all I got to do. The thing we have to be careful about is our units are going to have a mismatch here. If we plug in 1 milliliter divided by 23 millimeters times pi, wait, we've got something wrong here.
Yeah, I looked it up. I think it's r squared.
Yeah, there we go. I was like, wait a minute, the units aren't working out.
Yeah.
This is pi r squared. I think you gave me the circumference. Okay, let's rearrange that. We did circumference rather than volume. Pi r squared h. So then we can go ahead and say volume over pi r squared is equal to h. We're kind of in the same spot now. This is where we start to get in trouble. I can go ahead and say my inner radius. So another thing that's not given in the problem, is just assumed you already know it, is that 23 millimeters divided by 2 equals the radius. Right? Diameter cut in half is the radius. That's going to be what, 11.5? So I'm going to have 1 milliliter divided by pi times 11.5 millimeters squared equals h. Here's the problem. This is a centimeter cubed. Now, because it wants h, it wants h in millimeters.
Mhm.
So we've got two options for how we deal with this. I could convert the diameter to centimeters. I'd get the height in centimeters and then convert the height back to millimeters. That would be fine. Or I can just convert the volume to millimeters cubed, and then I'm fine. Either way I do it. Now notice there's either way works. I think it's easier to convert the volume. So we just have to make sure we pay attention to that as well, that we're paying attention to the volume. So we're going to have 1 centimeter cubed. How many millimeters in a centimeter? I can't remember either. Let's pretend I can't remember. I know it's 100 centimeters for 1 meter. And I know it's 1 meter has 1,000 millimeters. That's going to be 1 centimeter has 10 millimeters. I'm going to flip that over. So I have 10 millimeters per 1 centimeter. Does that all make sense? I just had to do a little memory check. I'm going to erase this now that I remember that it's 10. All right, so I knew it was 10. I just go with the things that I have an easier time remembering. Okay. Don't forget, I have to do this for all 3 dimensions. I have to do it for the x, the y, and the z. So I'm going to have to do that cubed. So that's going to be like 1,000. So then eventually I'll get back to the calculation we were trying to do. Great, so I'm going to have notice I'm going to have millimeters squared on bottom, cancel out 2 of my millimeters on top. I'm going to be left with units of millimeters now. And that should give me the height between the marks, which I'm expecting to be like 2. Let's see how it works out. 11.5 squared times pi inverse times, oh, anyone else get a number yet? No calculator? No, get a number.
For the bottom? Like
The whole thing, h equals. This is number 12 on 1.1. What'd you get?
I got 2.4.
That's what I got. We're going to call it 2.41.
Okay.
Right, because the 0.7 is going to round up. We've only got 3 sig figs. Technically, I think we only have 2 sig figs, but 2.4-ish.
Okay.
Right, which is about the 2 we were expecting. From like eyeballing, I don't even know if this was the right diameter, but that's kind of how we do the process. This problem, when people first see this problem, so I want to point out a couple things, and there's a lot of reasons why I like this, and I hope the people who are watching this got stuck on the problem before they're watching this. Because when you read this problem, like most people go, I have no idea how to start this. I don't know what's going on at all. And pretty much every problem you get asked in every class has this kind of setup where there's some information they give you that's explicit. They tell you what result they want you to talk about. And there's some little bit that's missing in between that they're trying to see if is in your brain or not. And so in this case, there was a lot of bits. The most important bit for our class was this unit analysis. I just assumed you knew the volume of a cylinder and you could figure out that volume and volume were equal to each other. That wasn't even supposed to be the hard part, but that's where most people get stuck. Because they don't have enough experience with a graduated cylinder to be like, oh, it's a cylinder, and I just need to know the volume. I know the volume is 1 milliliter, and I know the volume is this equation. Now I just set that volume equal to 1. Solve for H. Once we have this bit here, the rest kind of follows pretty easily, and the tricky part is the unit analysis. And the unit analysis is the part that I was really kind of trying to get at. But yeah, even your history classes will do something where they're like, what was important about the Battle of 1812? You know, they're telling us the Battle of 1812, and then they're trying to get you to say all of the things they want you to think about regarding the Battle of 1812. It's explicitly 1812, and everyone, of course, thinks of the United States Battle of 1812, but there were wars happening around the world at that time. Context matters. We're just, you know, we usually teach U.S. history and not other countries' histories. So, in any case, this structure, we'll see this come up. I'll do this in class every once in a while. I'll do this in office hours. We'll notice that anytime we're like, wow, I don't know where to start in this problem, I'll always start with well, what is the information that I'm given? What is the thing that it's trying to get me to? Can I recognize the implied information, the stuff that it's not telling me that it's trying to make me think about? And by finding those edges around the thing it's not telling us, sometimes it helps us point to it a little bit better. And this is a really good volume one. We had to make sure we were careful because we were doing that three-dimensional volume analysis. Now, number 13, let's work on that one later. I'll tell you the tricky part for number 13 is, do you know how to find the volume of a tube rather than the volume? So the inside, all of the air that's in there is a cylinder. How do you get just the glass part to get the volume of a tube? Do you remember from your geometry classes? I'll just tell you real quick. Big cylinder minus little cylinder. It gives you the volume of the glass.
So it wouldn't just be like 1 milliliter?
No, right? So that thing is asking, the number 13 is asking how heavy is this graduated cylinder. So we need to get the volume of the glass, so we can use density to get the mass of the glass, and we need it for all 100 milliliters. So it's going to be big cylinder minus small cylinder. So it's going to be outer diameter cylinder volume minus inner diameter cylinder volume to get the volume of glass. And after that, it's easy. But it's just, again, the funny part about this problem to me is I didn't mean the geometry to be the hard part, and the geometry is the part that's hardest for everyone. I meant it to be the unit analysis. And everyone's like, no, we took geometry a long time ago. We didn't know we would need geometry in chemistry. So, but that's the geometry part. Big cylinder minus little cylinder. Are there other questions from the homework, or did you want to see another like volume problem? Or?
Yeah, like stuff like this, I think.
Okay, let's see if we can make up another problem. I'm looking around the room. Okay, this is, okay, I'm going to make up a curiosity problem. I don't know the answer to, and we're going to see how we do with it. I was just looking around the room. Is it okay if I erase all this? Yeah.
Yeah.
I was just looking around the room and I was like, well, what's something silly we could figure out? So here's the funny thing that I want to figure out. What is the volume and mass of 500 pages So I don't know. I just looked around the room and I saw this. And I was like, oh, that's interesting. What's the volume and mass of this thing? Now, there's a couple things we have to figure out in order to do this. I know a piece of paper is 8.5 inches by 11 inches, but I don't know how thick each piece of paper is. Right? And so this is one of the funny things that I try to get my nephews. I've got nephews that are in like middle school, elementary school. I'm like, how do you figure out how thick a piece of paper is? How can we figure out how thick this is? If we knew the density of paper and we weighed this, we could find the volume, right? And we could say, well, I know it's 8.5 by 11. I could find the volume of like this dimension if I knew the density of this type of paper. There are different types of paper that have different densities, so that might be a problem. I'm going to do a little silly thing. Oh, I lost my ruler. That makes me really upset right now. Here's the other funny part. We usually don't think about how thick paper is, but if I take 1, 2,
Thank you.
you bet, see you. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 17, 18, 19, 20. Okay, here's 20 pages. And now I need a ruler. So I can figure out how thick 20 pages are together. Anyone got a ruler? I lost my ruler. Last quarter somebody borrowed it and left the room with it, and I don't even know who took it. So I lost my ruler. Awkward silence on the recording. I have nothing that is ruler-like.
We could go like ask.
Yeah, I'm trying to think of some way we can do it in the room. Let's see. How many times can I stack 20 pages across this? I just need to figure out how thick this is, right? How can we figure out how thick this is? How can we figure out the thickness of a single piece of paper? This is not what the problem is supposed to be getting us to do. Are you trying to Google it?
Yeah.
Because the problem is, what kind of paper are they going to be getting? So there's all kinds of differences depending on the weight of the paper. Right, so this is 20 weight paper. It's got a weight per meter squared, which is kind of weird. Oh, that's funny. It gives me the millimeters as fine thick as well. I can't. I'm so frustrated that that ruler is gone right now. I don't have another ruler or any sort of measurement device. Okay. I'm just going to make a total mess. Here's my idea. Oh, but I don't know how many pages this is. That doesn't work. Okay. The reason I counted out specifically 20 was to get specifically 20. Okay, let's ask for a ruler. Who's got a ruler?
Someone's gotta have one.
Someone's gotta have one. I should have one. Someone stole my ruler. Those of you watching at home, you can fast forward past this. Well, let's see if we can do something with this, actually. It tells me, that's weird. So the package says it's 75 grams per meter squared. It also tells me, hey, how's it going?
Good, how are you?
Oh, I'm okay. 21.6 by 27.9. It also tells me the dimensions of the paper, rather than telling me an 8.5 by 11, it says it's 21.216 meters by 0.279 meters. So I can get essentially it's weird that it gives mass per an area rather than mass per volume. So I think I can get the mass of one piece of paper. I think I found a way around from the information on the package. So it told me that it has 75 grams per meter squared, and it told me that each page was 216 by 279 millimeters, which is 0.216 by 0.279. So I can go ahead and multiply those two numbers together, 0.216 times 0.279, and I can get each page of paper has a surface area of 0.06026 meters squared. I can multiply that by 75. And that tells me each page weighs 4.51, I'll call it 4.52 grams. Doing a little bit of rounding. .52 grams per page. How is this going to get us to volume? It's like grams per surface area is such a weird thing. Only paper does this. It's the weight of the paper. Because you never really consider the thickness of the paper. So that tells us that 500 pages, so I can multiply that by 500. 500 pages is going to have a mass of 2259.9 grams, which is 2.259, we'll call it 6, 2.260 kilograms. Multiplied by 2.2, or 4.97 pounds. So 500 pages of paper is about 5 pounds. So one of those reams of paper is about 5 pounds. It'd be really nice if I might take a piece of paper to class tomorrow and weigh out a piece of paper and see if it actually weighs 4 grams. But that's why they refer to it in terms of the weight of the paper, like it's kind of the thickness, how heavy the paper is. And nicer paper is usually higher weight, has either higher density or it was a thicker piece of paper. How does this get us to the volume though? So I think, who's got an idea for how we get to volume? I don't think I made up a very good problem, but this is the trouble with making up things on the spot.
So is this is just the weight, or is it density too?
This is just how much the paper weighs.
Okay.
This is 500 pages of paper weighs that amount. We don't have the density right now. Could we get the density? So that's the thing, is there a way to get the density? Because if we had the mass and the volume, we'd have the density. We have the mass, We have the number of pages, but we don't have the volume. We have the area, but we don't have the volume. And I don't know if there's a way to put those things together to get it all. Maybe this was a bad problem to make up. So here are the things that I'm thinking about. Okay, so this is like, oh, let's say, what did I have? I had 4.52 for the mass of a single page. Let's just do 22599. Yeah, 4.5198 grams per one page. And I know the surface area of that. I don't think there is a way to get this without a ruler or a density of paper. Because we're just missing that volume aspect to it, right? We're missing that depth of it. I know that we've got 2259.9 grams per 500 pages. And I know 500 pages is going to look like a stack, right? Can I figure out? No, because this is done in this weird unit, I think we're stuck. I think we need other information to solve this problem. So I'm going to go ahead, I'm going to do that. I was trying to do it without Googling anything, but I'm going to go ahead and Google. Density of standard paper. 1.2 grams. Okay. There's, oh my goodness, I just got into like a weird world of like paper quality debates online. That's what I got when I Googled this, is like, how much does paper weigh? What's the proper weight for your printer? What's the proper weight if you're doing something like legal documents are printed on different things? Is there a standard density? Wow, this guy. Equipment compatibility, like there is, wow, I made a weird problem. It's giving me the, oh, that's funny too. Oh my goodness. This is like, I mean, this like unverified, okay, here we go. This is all a lot. Wow, this is a whole world I did not mean to get into. There's just like, people just are really into their paper. Okay, here we go. If we have 20 weight paper, the thickness is, according to this random site that I found, which I don't know if we should trust this or not, but is this even the right thing? Let me see here. Yeah, if we have 20 weight paper. So I had to Google something to get this to work because I made up a bad problem. But if you have the 20 weight paper, which is what we have, the thickness is approximately equal to, where'd it it go? 0.097 millimeters. Okay. Now we can go ahead and calculate the volume of this. So we got the number of pages, we got the mass of that block. Okay, we're gonna find the density of paper because I wish I knew this now. We're doing they asked for a problem, I made up a problem on the spot and it went really weird.
That's fine. I'm just here to figure this out too, so
Okay.
I'm good with that.
So let's go ahead, let's get our dimensions. I'm gonna go ahead, even though I had it in millimeters before, let's practice doing our conversions. I wanna save this number here, so I'm gonna just box that real quick so I don't accidentally erase it. Actually, I'll box this one at the bottom so I've got more space. Let's keep our thickness handy. Let me put thickness here. So it's like, I'll just call it height is 0.097 millimeters. Let's go ahead and calculate the volume of a single piece of paper, and then we'll calculate the volume of like an entire stack of paper. So we've got to take our 8.5 inches. There's 2.54 centimeters per 1 inch. I just happen to remember that one. Just comes in handy if you talk to people in other countries, knowing how many centimeters are in an inch. That's going to get me to centimeters. I'm going to do the same thing with my 11. So I'm going to take my 11, and I'm going to multiply, that's 11 inch times 2.54 centimeters per 1 inch. Both of these, I want them, since this is in millimeters, which way should I go? I like it in centimeters better because that gets us to like milliliters volume. I didn't say what unit I want this in. Let's go centimeters cubed. So I'm going to go ahead and convert this one. This is going to be 0.1 centimeter per 1 millimeter. Or if it makes you happier, we can do it this way too. We can do 1 centimeter as 10 millimeters. That same thing we did before. Now the reason we're doing this multiplication is so that our height is in centimeters, our width is in centimeters, our length is in centimeters. Everything will be in centimeters. Then I can just multiply the 3 together and that'll get me centimeters cubed.
I'm sorry, this is such a basic question, but and you just, based on like the chart and what we know, we just always just pull like how the 1 centimeter over the 10 millimeters.
Yeah, we did that one in an earlier problem.
Okay,
That's why
perfect.
we grabbed
And
that one so
the
fast.
same with the 2.54.
The 2.54, I just knew you would look
Okay,
that up.
perfect.
Yeah.
Thank you.
Hey, come on in, grab a chair. Okay, so now we can
sorry,
just,
that's, like, literally right.
let's go ahead, grab, all my calculators ended up all the way over there. Get your calculators out too. Always good to double check your calculator.
I need one.
There you go. I mean, don't take it, but there you go.
No,
for
yeah,
now.
I'm taking
Yeah,
it.
yeah. So let's just do all these numbers, and then we're just going to do length, width, height is going to give us our volume. So, someone get length and width. I'll get height. That's going to be 0.0097 centimeters. Anyone get length yet?
I think I'm doing it right. Length is which one? The
Either one, just the 8 or the 11. I was thinking the 8 was the width and the 11 was the length, but either one works.
For the 11 inches, I
Mhm.
got 27.94.
I believe that.
For the 8, it's 21.59.
Yeah, that sounds great. 279, 216, yep. Okay, so now we go ahead and multiply this all across. 27.94 times 21.59 times 0.0097. And we get, this can't be right. Oh wait, no, this is totally right, okay. It's the volume of a single piece of paper. I was thinking of the whole 500-page stack. So we get 5.85 centimeters cubed. We get like 5 milliliters. So this is kind of funny. If we took a piece of paper and we crumbled it up as small as possible, like turned it into a powder, and filled it, it would fill like that much space, about 5 milliliters. It's funny to think about like how big it is. If you made it, if you crumbled it, so like, the problem with crumbling it is there's like a bunch of air caught in there, so you're not really getting it down to its smallest possible volume. You'd need to like compress it in some way where like you got all of that air out of there. I guess if I folded it really nicely, as fine as possible, you could get it down to like 5 milliliters. Even this, there's still air trapped in there, but you can get it down to like 5 milliliters of volume. So now if we do 500 pages, that's per page. And then we have 500 pages. We take that 5.85, 5.85 times 500, and we'd get oh, that's a weird 9. 2925 centimeters cubed, which is like 3 liters. That also doesn't sound right. Does a ream of paper seem bigger than a 2-liter bottle? I guess it is, right? Because the 2-liter bottle is like really narrow and tall.
Yeah.
I guess it is more than a 2-liter bottle. Interesting. So yeah, that was kind of just a little funny problem. This is why I usually don't make problems on the spot. I have to like pretty carefully pick my problems. Otherwise, we end up in these really like weird tangents. Okay, should we do another volume one that I make up on a spot? No? Well, I've got a volume one to make up on the spot that I think is more interesting. Let's see. No, that's not going to be interesting. Okay. We're going to put it in an above ground pool. The above ground pool is a rectangle that is 86 inches by 36 inches. And we want it to be we got a pool. I just Googled above ground pools. I grabbed the first one that came up on Amazon. It's a cheap $100 to get an above ground pool that is 86 inches by, not 23, 30. Yeah, let's do bigger than theirs. I picked a bigger pool. It's 86 inches by 36 inches. That's what, like 3 feet wide and like 9 feet long, and I want it to be 5 feet deep. What volume of water could it hold? Calculate. I'm gonna do it. Oh, we'll see how you all do it. How are you all approaching it? You don't know how to do this one, or you're not interested in? Are you here for something else, or?
I mean, I'll always do this.
Oh, okay,
I'll
okay.
always practice.
Yeah, I don't want. You don't have to. I'm just curious. How are people approaching it?
I'm not too sure how to approach this.
Oh, it's like I was gonna approach it like a cylinder, but like the picture's kind of like a square.
It's a square, right? It's a square. Oh yeah, it's not one of the round ones.
Yeah.
Yeah, this is a square above ground pool, not one of the round pools. That's why it's 86 by 36. It's not just a radius.
I'm just going for it. I'm just kind of pulling things from the previous question and seeing where it takes me. Ish.
First thing we should notice, do you all know what that double mark means? The 86 double mark by 36?
Inches?
Yeah, that's
Inches.
inches.
So
Yeah,
I
that's
converted
inches.
5 feet to inches. So that's
Perfect
all the
start, right?
same.
So we've got 86 inch times 36 inch. 5 times 12 is 60 inch.
Yeah, that's what I did first.
Right. First thing is we have to make sure our units are matching. If our units aren't matching, we're going to be in trouble. So at this point, I can do those multiplications, and I can get inches cubed. That's a totally fine way to do the problem. Right? And this is part of why I picked a square pool. I didn't want us to have to worry about like pi r squared and stuff like that again. So I picked a square pool. So we're going to have 86 times 36 times 60. Oh, I missed a digit there. 86 times 36 times 60. Whoa, that's a lot of inches. Whoa, that's a lot of inches. So that's 185,760 cubic inches. So that's a lot of cubic inches. Now let's think, well, let's not think about that yet. Let's just go with it and see how it works. Well, I mean, how big's a gallon of water? Like, think of a milk jug, right? That's a gallon of milk. How many milk jugs could you throw inside it? Like, if you had an empty pool, how many milk jugs could you stack inside of there?
Like a lot.
A lot. A lot. Even if it's a pretty small pool, you can still stack a lot of milk jugs in there. So right now, we've got this in inches. We want to get it to milliliters, and we can think about it in liters and gallons if we want to. I always like to think of it in some like contextual way like that. We got to get this to milliliters.
So do we just have to put it into like cubic meters?
Yeah, there's two different ways to go about it. We could take each of the inches and convert each of the inches to centimeters, or we can just convert the cubic inches to cubic centimeters. And since we already did our multiplication across, it's going to be easier to do this one. Right? But I'm going to show you both just so we can see how it works out. I could do 86 inches times 2.54. This is how we did the last one, right? 2.54 centimeters per an inch times 36 inches times 2.54 centimeters per an inch times 60 inches times 2.54 centimeters per an inch. And if you notice, I've got 86 times 36 times 60 again, and I've got 2.54 times 2.54 times 2.54. I've got 2.54 cubed. So this gets us to the other way to do it, which is the 185,760 inches cubed times 2.54 centimeters per an inch cubed. I got to cube that number, that unit, and that unit. And that should get me my total volume in milliliters. Again, what I said last night in class was I make less mistakes when I convert the individual dimensions. So this long way of doing it, that's the way that I usually do it. I make less mistakes that way. This shorter way also works. I just make more mistakes when I do it that way. So I have to be extra careful if I'm trying to be fast.
I'm sorry, I'm just trying to still figure this all out in my head. So technically with the longer equation in blue, you could look at it as like putting each of the sets in parentheses, doing them separately, and then combining it.
Centimeters.
Okay, perfect.
Yeah.
Thank you.
Yep. So I'm going to do 2.54 to the power of 3 times 185,760. I'm going to put this into scientific notation because it's getting so big. 3.044 times 10 to the 6 milliliters. Divided by 1,000. Oops. That's 3,000 liters of water. How many gallons does that work out to be? Do we have that conversion of liters to gallons on here? I don't think so because we never use it.
Wait, so after conversion, you multiply the 3 product?
Yeah.
Okay.
And let me know if you get the same number that I got. I think you will. It's about 0.26 gallons. 1 liter is 0.26 gallons. So I'm going to do 3.044 times 10 to the 3, 0.26. So that would be 790 gallons of water. Is that reasonable for a pool going swimming? Yeah. Have you ever seen how big fish tanks are? Like a 20-gallon fish tank still takes up like an entire counter. So to have a pool that we could actually swim in, having like 800 gallons of water makes sense. Now, just for a reality check, I'm going to see if the Amazon listing tells us, oh, well, their pool's terrible. Their pool is, what is that? Their pool's only 2 feet deep. Who wants to swim in a 2 foot? Whatever the case. I want to see if they've got in the extra information, if they tell us how many gallons it is. How much it weighs. In frame. Capacity is 1,662 liters. Since our pool's about twice as deep, we get about twice as much volume.
So I got the answer, but I want to know how to put it in scientific notation.
Oh, how comfortable are you with scientific notation?
I've
Not
never
comfortable.
taught it.
Oh, wow, okay.
Yeah.
So we'll talk about this in class tomorrow as well. Here, I'm going to do that up here. Is it okay if I erase the problem? Was that a better volume problem?
Yeah.
Okay, cool. Yeah, I was like, let me pick one that I actually know is going to work out rather than the random paper thing I did. Okay, so scientific notation. The way it works out is, so we get this answer of like 3044.
061.009.
Right, so I'm going to forget the 009 because that's like whatever. Right?
Okay, yes.
So what I do is I say, okay, I've got my decimal point here, and then I just go 1, 2, 3, 4, 5, 6, 3.044061 times 10 to the 6. And then I can more easily represent which things are significant and which things are not significant. Since I only had 2 digits in each of my things, right, I can't remember the inches now. It was 86 inches by 36 inches. I should really say that this is approximately equal to 3.0 times 10 to the 6. And now it's really easy to see I've only got 2 sig figs there. If I wanted 3 sig figs, right, versus if I tried to write this out as 3.0, if I tried to write this out as approximately equal to 30, which of those zeros are significant? Which of those zeros are not significant? It's ambiguous. It's ambiguous to me, right? Like, how would I communicate 2 significant zeros with that number? With our typical way of writing numbers, it's either all, like if I put this decimal point here, all of those zeros are now significant, right? If I don't have that decimal point there, none of those zeros are significant. So how do I communicate one of the zeros? Only the first 0 after the 3 is significant. You have to go to scientific notation to really do that in a reasonable way. If I want to show that 2 of the zeros were significant, I write it as 3.00 times 10 to the 6. Now I've got 2 significant zeros.
But either way is fine in this case.
What do you mean either way is fine?
The correct answer.
So the correct answer would be this one where we've only got
Yeah.
2 sig figs because all of my measurements only had 2 sig figs.
So you base it on the context.
Yes, absolutely. Always based on the context. That's the most important thing for sig figs is, you know, how did you make your actual measurements? What's the actual context? Like, everything we do in a chemistry class has context. It's not just, we'll follow these random math rules. That was the thing that always got me was, I first learned about sig figs in a math class where it was just these rules I had to follow. And I didn't really understand why. And it wasn't till later in chemistry and physics classes where they're like, no, it's because it's in the context of a physical problem. That's why you have to keep track of it. It's how well you made your measurement. It's how well you know the information. Right? I don't know how well they make these pools. Are these pools made to exactly 86 inches or are they made to 86.00 inches? I don't think they're making them that well. Plus then when I get it in my backyard and I try to set it up, is it going to go to a perfect square with the perfect side lengths? It's probably going to be about 86 inches by 36 inches. It's not going to be exact. Right? It's not going to be 86.0. And so as we report our numbers, we're reporting something about that context. Okay, now that there's some other people here that weren't here earlier, do you have specific questions for any of the homeworks? Or?
No, I just came to
Okay.
trying to see where other people were. The
Great,
questions.
great. Yeah.
We go over number 2 on the homework.
Sure, what is number 2? Before we get to that, are we okay with this?
Yeah.
Any other questions? Okay, so let's go ahead, let's get rid of this. And let's look specific. This is on MQ 1.1 still?
Uh-huh.
Okay.
It's what is 2.5 kilograms over microliters in grams to milliliters?
Was that 1 microliter?
Yeah.
And we want to get it to?
Grams over milliliters.
Okay. So, how do we do this? Do me a favor, you've already thought about it some, but those of you who haven't thought about it yet, take a moment and think about it.
How do you pronounce the one? Is it mu-L?
Microliters. Yeah. But it is the Greek letter mu.
Yeah.
Yeah. But we just say micro. Okay. Give me a sideways thumb when you're feeling a little stuck. Yeah, you started stuck. It's okay. Hopefully you're working at it on home as well. You're not just fast forwarding. Probably fast forwarding.
I think I'm stuck.
Okay.
Like maybe something.
Okay. So let's go ahead. So these problems where we've got these fractions, we can really break it into, let's deal with the top, then let's deal with the bottom.
That's what I'm doing.
Yeah. So I'm going to go ahead and I'm going to take my 2.5 kilograms. How do I convert kilograms to grams?
There's 1,000 grams in a kilogram.
Oh, I did 100 instead of 1,000. Okay, that will get us to grams on top. That'll get us 2,500 grams. How do we get from microliters to milliliters? Now this one was on the, it's in the textbook in chapter 1. It was also on the slide about volumes because microliters does come up every once in a while. Micro means 10 to the minus 6. So if I'm thinking milliliters, I think that means that if I have 1 milliliter, it's going to have 1,000 microliters inside of it. Now let's talk about how I did that. Okay, so the things that I know is 1,000, let's do this. We got 1,000,000 microliters per 1 liter. Right, because that's 10 to the 6. 1, 2, 3, 4, 5, 6, 10 to the minus 6. 10 microliters. 1,000,000 microliters per liter. And I know that in 1 liter, there are 1,000 milliliters. So if I multiply that across, I cancel out my liters, I get my microliters, and I got to make my micro look more like a micro, less like an M. So my microliters per liter, that's going to get me 1,000 microliters per 1 milliliter. And then I need that flipped over so I can cancel out my microliters and keep it in milliliters. If you didn't know how many microliters per a liter, that's something we'll work on more tomorrow in class, but it is also in the textbook. There's those Latin prefixes. There's a few that we use really commonly. It's the centi, the milli, the micro, the nano, and the kilo. So this is a 10 to the 3. This is a 10 to the minus 2. This is a 10 to the minus 3. This is a 10 to the minus 6. This is a 10 to the minus 9. Those are the 5 common ones that we use this quarter. There's dozens of others, right? Most people know gigabytes at this point because that's where computers are. Terabytes, gigabytes, kilobytes. Those are all bigger numbers. Chemistry mostly deals in the smaller, the centi, the milli, the micro, the nano. And if we wanted to, we could go to the pico. We don't use this one very often, but that's 10 to the minus 12. And then we can also go to the femto, which is 10 to the minus 15. Again, we don't really use that one. Pico and femto we don't really use, but there are more. These are the 5 that we're going to use really often. And you notice there might be something confusing here because I got micro as 10 to the minus 6, but I've got it as 10 million here. That's because if I wrote this, if I flipped this over, the other way I could write it is I could write 1 times 10 to the minus 6 liters equals 1 microliter. That'd be like 1 over a million. And so when we write it like this, the micro means 10 to the minus 6. We're writing 1 times 10 to the minus 6 liters is 1 microliter. Which, if I divide this over, that's going to give me 10 million, that's going to give me 1 million microliters per liter. Whatever the case, the point was that I could get to this conversion where it's 1,000 microliters per milliliter. Are we good with that?
I'm kind of stuck because so you divide 1 by 1,000 and then you get 0.001. Right? So what do you do with that?
So that's the next step. I just wanted to make sure we were good with this conversion that I came up with from the Latin prefixes, micro and milli. We good with that?
Yeah.
Okay. Again, this is something, these 5 we do have to remember, that is a memory thing. So make sure you're working on that. We use them really often, so hopefully it'll become common. This gets us 0.001 milliliters. Right? And then I just have to take these 2 things and divide them by each other. So then I'm going to have 2500 grams divided by 0.001 milliliters. I'm going to plug those numbers in and see what it gives me. Oh my goodness. Do you see what's going to happen? Look, our top went up by 1,000, our bottom went down by 1,000. Guess what we get? What'd you get?
2,500,000 grams over milliliters.
Yeah, something massive. So I'm going to go ahead and call that 2.5 times 10 to the 6 grams per milliliter. Right, again, introducing this idea of scientific notation. There's a couple reasons why we do scientific notation. It's more condensed, it's easier to write down. 2.5 times 10 to the minus 6 is easier to write down than 2.50, 250,000, right? 2.5 times 10 to the minus 6. It also, more importantly than it's easier to write down, is it makes it really obvious I'm working with 2 sig figs here. I could just as easily write this as 2.50 times 10 to the 6, and now I've got 3 sig figs, but it's the same number. So scientific notation makes it really easy to show our significant figures. But that becomes our final answer, that 2.5 times 10 to the minus 6 grams per milliliter.
And just out of curiosity, like you said, like pulling context from the question to decide the number of significant figures.
Yeah.
Did we determine that by the 2.5 kilograms?
Correct.
Okay, thank you.
Yeah. Since it was 2.5 here, they only gave us 2 digits. We kept that 2 digits in our final answer. All of these, like this micro to milli thing, these are all definitions, so they have infinite precision. They're never going to limit our sig figs.
And in lab, how you can put like either the scientific notation or not.
Yeah. The thing you have to be careful about is don't use X, the letter.
Use E.
Use E, or you can use the multiplication sign. But X, if you use the letter X, it thinks you're like writing a word. So you have to use, like, I think it's shift 8 for the star. That means multiplication.
Okay.
Otherwise, it's like, I don't know what 2.5 x 10 6 is. Because it's trying to read it like a word.
And then for like to the 6, do you just do like the little like
Caret.
Yeah, okay. I was
Yeah. The little hat thing.
I was like, this one?
Yeah, it's called a caret.
Okay, perfect. And then just do grams per milliliter. Or do you have to write
You don't
that?
need to use the units. The units are often included in underneath the
I
box.
feel like that's fine. It has
Yeah.
to be right here.
Oh yeah. So go ahead and hit evaluate.
Okay,
Yeah.
perfect. Thank you.
Now, you can use that times 10 to the 6, or you can use the capital E.
Mm-hmm.
That means times 10 to the 6 as well.
Okay.
Or I mean, that means times 10 to the.
Okay.
So there's 2 different ways you can write this down in LabPal, that LabPal understands it. You can write it as 2.5 star 10 caret negative 6. Or you can write it as 2.5 E minus 6, and it'll also understand that.
Okay. Perfect.
Or you could write it down as 2.5. It'll also understand that,
Okay.
of course.
Yeah.
But when we're doing things that are like 10 to the minus 9, you don't want to try to count all of those zeros.
It's telling me I'm incorrect.
Let me see what you got here. I'll use capital E. Lower, like, yeah, try it with capital E. Let me
Wait,
see.
I do it with lowercase e.
see something really quick. What's going on here? Why is that telling you incorrect?
Could I refresh the page maybe?
You got kilograms per. I'm just trying to make sure that it's not like doing something different. Oh, because I wrote the wrong thing on the board. Positive 6. It's not negative 6. It's millions, not micros. Right here in the box, positive 6. That was all.
6 attempts.
Because you were copying from the board. Don't trust me.
No,
I'm human. I'm flawed.
I wrote positive 6.
Ah! We both did it. I'll give that warning of these positive exponents really mess me up because chemistry so often works with negative exponents. Like my hand like defaults puts the minus signs in there. It's really a habit I've got to break.
Do you think you could go over one similar to 15 on the homework? I know it's a graded question, so I don't know if you can do it exactly, but just practicing with the UM to the CM.
Yeah.
I'm so confused by this.
Yeah, so
you
let's
can't do like an exact one.
I can do it. I don't mind.
Okay.
So this is MQ1.1. This was number 2 that we just finished. I forgot to write that. It was number 2. This is number 15.
Yeah.
So let's go ahead and look at number 15. I'm going to erase all of this, yeah? Okay. So, let's see. I can change the numbers a little bit if it makes you feel better. But what do we have?
Convert 127 cubed to centimeters cubed. I don't know if it's pronounced. Or is that microliters?
That's micrometers
Okay,
cubed.
yeah, see, I don't even know how to
Yeah,
say.
no, you did fine. Micrometers cubed. I knew what you meant by cubed as well. Okay, so again, the thing that we have to keep in mind here is how do we convert from micro to centi? So I know in my head, but I still mess it up, so we're going to be careful and we're going to do a little quick check. I know that it's 1,000, sorry, not 1,000, it's 1 million micrometers per 1 meter. And I know that it is 1 meter has 100 centimeters. So if I multiply that across, I'm going to cancel out 2 zeros. I'm going to have 1, 2, 3, 4 micrometers per 1 centimeter. So there's 2 different ways I could write this down. Right? I can write this down, well, we'll just leave it like this, right? I'm going to say 1, 2, 3, 4. So this is 1 times 10 to the 4 micrometers per centimeter. And that was kind of the main step of this problem, was just making sure we're learning those Latin prefixes, learning how to relate these Latin prefixes, micro to centi, to get some conversion factor. That's part 1 of the problem. Now, I'm in micrometers and I want to get to centimeters. So I'm going to go ahead and flip this thing over, and I'm going to have 1 centimeter per 1 times 10 to the 4 micrometers. And I'm going to do one other thing just to show you. Right, and that's positive 4, okay, yeah.
So you can just like flip it if you feel like it.
Yeah, because it's still just a value of 1.
Oh, okay.
Right? Whether it's the thing, either way, it's still just a value of 1.
Okay.
Now, one other weird thing we could do, because I like having my numbers on top of the fraction rather than on bottom of the fraction, you could also write it as 1 times 10 to the minus 4 centimeters per 1 micrometer. So if you bring this 10 to the 4 up top, it's just a 10 to the minus 4. You can plug that into your calculator, see the same thing happen. If I do 1 divided by 10,000, I get 1 times 10 to the minus 4. So, and I like writing it this way just because I like my numbers on tops of the fractions. I'm less likely to make a mistake in my calculator if everything's on top. But you can do it this way fine as long as you're careful with your parentheses. Either way works. In your calculator, if you're not careful, this 10 to the 4 could come up on top and get multiplied the wrong way.
So when you're dividing, you just have to make sure you start it before you write the
Yeah.
notation.
Yeah, you just have to be careful in your calculators. On the board, on paper, I know what you mean, but the calculator doesn't know what you mean if you hit the division at the wrong time. It's a particular problem in the fancier calculators, like these calculators, because like the way they do fractions, the multiplication automatically gets thrown on top if you don't do a parenthesis. It's a total headache. So got to watch out for that. But either way works. Let's go ahead and keep it like this just for now because I think that's more comfortable right now, even though I like this way better. So I'm going to go ahead.
Why you did the 10,000, you just put that in scientific notation and that's how you reword. Okay.
Yeah. So I just rewrote this 10,000 into scientific notation because I prefer scientific notation. Yeah. Easier to punch into the calculator, easier to keep track of things. This looks like one sig fig, but remember, since these are definitions, this is actually an infinite number of sig figs. This would be like 1,000,000.0000000 forever. I just didn't feel like writing zeros forever. So now I can go ahead and do my multiplication. I'm going to have 127 micrometers cubed times 1 centimeter per 1 times 10 to the 4 micrometers. That does it one dimension. I have to do it a second time to get the second dimension. Then I have to do it a third time to get the third dimension. So I'm just going to do it cubed to get all 3 dimensions. So that will get micrometer cubed, centimeter cubed, and wow, it's going to be a really small volume. Punching it into the calculator. I'm going to start with just doing this part, and you can see I wish. Okay, so we'll do 1 times 10 to the 4, power of 3. So that's going to be negative 12 times 127. What'd you get?
I'm still trying to figure it all out. Sorry.
Oh, okay.
I'm like still. Wait, I'm sorry. I'm just a little confused. So we're doing the cube of like parentheses square, the little 3 up there. Sorry, because we're trying to get it to centimeters cubed. Correct.
Yes, right.
Okay.
And so we need to convert micrometers 3 times. So I need to use this conversion 3 times. So I need to multiply by this by once for the first dimension, twice for the second dimension, 3 times for the third dimension. So I have this cubed, so it's like multiplying by it.
Okay.
Not 3x, but it's that times that times that.
Okay. Sorry, you go.
I had a different number for this
Yeah.
problem, but I got 1.69 times 10 to the negative 10.
That's about what I was expecting. So,
are we just like kind of doing that thing where we like cross off the?
Absolutely.
Okay, so like cross off the bottom and then the 127
Yeah,
thing.
so when this cube comes in, right, what happens here is this cube is going to cube everything inside this parenthesis.
Okay.
So I'm going to have 1 cubed times centimeter cubed divided by 1 times 10 to the 4 quantity cubed micrometer cubed. Right? Everything gets cubed. Make that parenthesis a little bit bigger. Right? So then that's what allows me to cancel out the micrometers cubed and get centimeters cubed left over.
Okay, perfect. So then you're gonna essentially, it'll turn into 127 over the 1 times the scientific notation bit.
Yeah, so this
Okay.
is going to be divided by 1 times 10. The 3 times the 3 and the 4 get multiplied together, and this becomes a 10 to the 12 on bottom.
Okay.
Which the same way I flip this over, it's like a negative 12 on top, and so you end up with 1.2 times 10 to the negative 10.
Okay.
Calculator it though. I do an okay job seeing numbers in my head, but don't let me go too fast. Always tell me to slow down. Are we following? Is it good?
Yeah.
Yeah.
We still have like 10 minutes left in office hours. Do we have any other specific questions? I think I'm going to stop recording now and I'll get that uploaded, so if you need to rewatch any of this, you can.